Alright, so today's lesson is on the derivative of trig functions, the derivatives of trig functions. Alright, as you can see here, we got sine and cosine graphs going on. Alright, we also have a spring going on down there. We'll get to that later when we get to applications. So that's it, derivatives of trig functions. Let's get started. Alright, for the first one we're going to do is the derivative of sine. Hold on a second. Wait for it. You can skip through this if you want to. Here we go. It opened up my eyes, I saw the sign. Without understanding, I saw the sign. And it opened up my eyes, I saw the sign. Okay? Now you can make fun of me again for singing on the video. Alright, so let's find the derivative of sine. Okay, for the first couple, we're going to derive them, figure out what they are just by using a little intellect that some of us have, some of us don't. So just follow along, and then we'll talk about memorizing them and actually using them. Alright, so this right here is the sine function. Alright, just kind of as a review, when we draw the derivative graph, alright, we're looking for, hey, what is the slope of this graph? And that translates to a y value on the actual derivative graph. So let's think about a couple of places here that we can see for sure. All right, right here at pi over 2, I'll even do a little xy chart over here. Function and the derivative. I probably won't even use that column. I'll know I'll put it there. All right, so let's look at a couple places. First off, we can see right here at pi over 2, our slope right there is 0. So an x of pi over 2, the normal function's up at 1, all right, but the derivative of that function is 0. All right, you can also see here at 3 pi over 2, and at negative pi over 2, and at negative 3 pi over 2, we also have slopes of 0. Okay, the graph goes from going up to going down. So it has slopes of zeros right at those places. So again, at what? I guess we could say negative pi over 2. All right, that y value would be a negative 1, but the derivative value would be 0. All right, at 3 pi over 2, we have a function value of negative 1, but a derivative value of 0. Okay, and then also at negative 3 pi over 2, all right, we had a y value of, let's see, 1, but a derivative value of 0. So that means for each of these x values, when I draw the derivative graph, which I'll draw here in, let's say, orange. Well, let's not do orange. Let's do red. Okay. At pi over 2, the derivative is 0. So I have a y value here for the derivative. All right, at 3 pi over 2, I've got a y value of 0. Here's me a derivative value of 0. At negative pi over 2, I have a slope of my normal function of 0. So my derivative value is at 0. And at negative 3 pi over 2, again, my slope of the original function, the sine function, is 0. So the derivative function is going to be 0 there as well. All right? Now let's figure out what's happening in between these. Between negative pi over 2 and pi over 2, what is the slope of this graph? Okay? Well, it looks like it's doing what? It's positive. It's going up. All right, but it's not quite as positive. As positive as it's going to get, and then not quite as positive until it gets back to 0. All right? In fact, right here at 0, the slope right there is actually going to be 1. All right, so what happens there between negative pi over 2 and pi over 2, since my slopes are positive, on the derivative graph, my y values are going to be positive. All right, and they're getting a little bit more positive until I get to 0. At that point, I reach as steep as I'm going to get on the regular function. And so it reaches a point of 1, and then it comes back down. Okay? Notice all of these values are above the y-axis because between negative pi over 2 and pi over 2, my slope is positive. It's increasing. All right, now what happens between pi over 2 and 3 pi over 2? Well, sine graph is going down. Okay? It's starting not quite as negative, pretty negative, and then not quite as negative until I get back to 0. All right, actually, it turns out that at pi, the slope there is actually going to be a negative 1. So the way that derivative graph looks is like this. All right, if we do the same thing over here, between negative 3 pi over 2 and negative pi over 2, my graph is going down as well. So my y values, or my derivative values, are going to be below the x-axis. All right, same type thing going on that was over here. If we continue out a little bit further, past 3 pi over 2, my graph is doing what? Yep, it's going up. So my y values for my derivative are going to be also positive. So it's going to look like that. Same thing over here. Okay? Between, looks like negative 2 pi and negative 3 pi over 2, my graph is going up. So my derivative values are going to be positive, and it's going to look like that. All right. Now looking at that red function, that derivative function. All right. Do we recognize what that graph looks like? It's almost the sine function, it's just been shifted over. All right, but if you pay careful attention to this part right here, starting at 0, then it goes down, crosses the x-axis at pi over 2. It's a negative 1, its minimum value at pi. Comes back, hits the x-axis at 3 pi over 2, and then goes back up. If you just look at that green part, we should recognize from last year that that is the cosine graph. Okay, remember Karate Kid cosine graph? And so that's what turns out, interestingly enough here, that the derivative of the sine function is actually the cosine of x. The derivative of sine is cosine. All right, let's take a look at the next one. All right, the derivative of cosine. This is your next slide. All right, we can do the same type thing here. All right, this one has, let's see, slope values of 0, at 0, at pi, and at 2 pi. And again at negative pi and negative 2 pi. All right, so it's going to be crossing the x-axis. The derivative is at negative 2 pi, negative pi, 0, pi, and 2 pi. All right, and if you're looking carefully, you might realize, hey, well, that's where the sine graph crosses the x-axis. So what are the chances that the derivative of cosine is sine? Because the derivative of sine was cosine doesn't work the same way. Well, not exactly, almost. All right, again, let's analyze the slopes of the cosine graph. Between 0 and pi, the graph is doing what? Going down. So the y values, which I'm drawing here in green, the derivative values are going to be negative. They're going to be below the x-axis. So what actually happens here is it actually looks like this. My slope values are going down, so my derivative values are negative. All right, after pi, between pi and 2 pi, the cosine graph is going up, and so my derivative values are going to be positive. So it's going to look like this. All right, if I do the same thing over here, between negative pi and 0, my graph is going up. So my derivative values are going to be positive. Okay, going like that. All right, we can do the same analysis as, hey, not quite as positive, pretty positive, not quite as positive. All right, but we saw that on the sine. You can hopefully get that. And between negative 2 pi and negative pi, my graph is going down. So my y values for my derivative are going to be below the x-axis. All right, so that graph that I've drawn here in green is the derivative of cosine. All right, well, let's look at it. Let's just look at starting at 0. Starting at 0, the graph goes down first, and then it goes up, and then comes back down. All right, so that's almost, well, that's not the sine function, is it? Or is it? It's not exactly the sine function. It's actually the sine function flipped over. So what turns out here is that the derivative of cosine is actually not sine, but it's a negative sine. The derivative of cosine is negative sine. So the derivative of sine is cosine, but the derivative of cosine is a negative sine. All right? We'll see that in a little bit. You're just going to have to memorize these. Okay? Hopefully this helps you understand it. Gives you a little hook to put in your brain to figure it out on. But really you just need to memorize it so you can use it. All right? And one last derivative we're going to derive. All right? And it's tangent. We're going to do a little bit different. We're not actually going to graph it because the graph would just look horrible. All right? But as you can tell in your notes, I said, hey, let's derive the derivative by trigonometric identities and the quotient rule. So let's do it. All right, the derivative of tangent. Hopefully you remember from last year in Advanced Math Plus. Yep. Tangent is the same thing as sine over cosine. All right, you probably also saw that in your ACT math review a couple of days ago. All right? Well, if I want to take the derivative of sine divided by cosine, I've got to use the quotient rule. Okay? And let's remember the quotient rule. The quotient rule is low, d high, minus high, d low, all over low, low. If you want to hear me sing, you can go watch the video on quotient rule. I'm not doing it again. All right, so let's do this sine over cosine. Let's find its derivative using the quotient rule. All right, so it'll be the low, which is what? Cosine. The derivative of the high, we just said the derivative of sine is what? Cosine itself. Minus the high, which is sine, times the derivative of the low, so the derivative of cosine, which we just saw on the previous page, is actually a negative sine, all over the bottom squared, so cosine squared. All right, we clean this up a little bit. On top, we got cosine times cosine, which is cosine squared. We have a negative sine times a negative sine, so it gives me plus sine squared all over cosine squared. Well, that's kind of ugly. There's a lot of stuff there. We'll probably make it simpler. All right, but again, you got to remember trigonometric identity. This cosine squared plus sine squared, that's one of those Pythagorean identities. If you got sine squared plus cosine squared, or just the opposite because addition is commutative, then this is the same thing as sine squared plus cosine squared, and that is actually equal to just 1. So the whole top part becomes 1. The bottom remains cosine squared. And then one other trig identity you got to remember here is that if you have 1 over cosine, that's the same thing as secant, because cosine and secant are just reciprocals of each other. So 1 over cosine squared is the same thing as secant squared. All right? And so that has proved for us, or we figured out, that the derivative of tangent down here at the bottom, something we need to memorize, is equal to secant squared. All right? So that is the derivative of tangent. All right, so whether you liked any part of that video or not so far, I don't know. Really care less. Hopefully that helps you out a little bit, help you memorize. These are the 6 trig functions: sine, cosine, tangent, cotangent, secant, and cosecant, and their derivatives. We've already found these three, sine, cosine, and tangent. And if you really want to, you can go and you can do similar things with secant, cotangent, and cosecant by doing some derivative rules, which we already know. All right? You can do that on your own if you want to, or you can ask me come during my 8th block. All right, but we just need to memorize these. Okay? Derivative of sine is cosine. We already got that one. Derivative of cosine is a negative sine. Derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. Derivative of secant is secant tangent. And the derivative of cosecant is a negative cosecant cotangent. All right, and you just got to memorize. There's 6 of them. Okay? So 6 more things you got to memorize. All right, now it's a little help in memorization. Okay? Hopefully you're just going to memorize sine goes to cosine goes to negative sine. All right, and then maybe the tangent is secant squared. Okay? But let's look at some things, some patterns to notice. Notice that when we take the derivative of all the co-functions, each of those start with a what? Each of them are negative. All right, so if we're trying to find the derivative of a co-function, a cosine, a cotangent, or a cosecant, it's going to start with a negative. All right, so if you have derivative of cos, you got negatives. All right, so you might want to write that down there. Derivative of cos, you got negatives. All right, and then you can also notice some other things. Sine goes to cosine goes to the negative because it's co, and then it goes to sine. All right, as for the other, you can memorize these in pairs. All right, tangent goes to secant squared. All right, and cotangent goes to something very similar. It's got the negative because it's a co, but instead of going to secant squared, it goes to cosecant squared. So tangent to secant squared, cotangent, because it's co, we have a negative, and it's going to go to cosecant squared instead of secant squared. All right, you can notice the same type similarity on these last 2. Secant goes to secant times tangent. Cosecant goes to a negative because of the co, and then cosecant, cotangent. All right, so if you can memorize them in these 3 pairs, remember that the co's go to negatives, that'll hopefully help you memorize them. All right, because you just need to memorize them so you can work derivative problems. All right, now let's actually get to some examples. All right, example number 1. All right, find the derivative of the function x to the 5th times cosine x. All right, this is where actually using the product rule is a little bit better than all that garbage stuff with all the different, hey, x to the 5th plus 3x times x to the 3rd minus 2x, which we could, if we really wanted to, FOIL it out and then do it. This is a little bit more interesting as far as that goes. So let's do it. We should realize that this function here has 2 parts. Okay, it has an x to the 5th, that's part number 1, times the cosine, which is part number 2. All right, so I've got 2 parts that are multiplying, so that's going to use the product rule. So to find the derivative, all right, with product rule, okay, in some order, I take the derivative of the first. All right, that just involves a power rule, so that turns into 5x to the 4th. All right, and you leave the second part alone. So derivative of the first, we'll leave the second part alone. Plus, leave the first part alone and take the derivative of the second. So the derivative of cosine, if you remember, it's got a co, so it's going to be negative, and cosine goes to sine. All right, and that's almost it. You see, I need one little cleanup of it. I'll leave the first part alone. 5x to the 4th times the cosine of x. All right, but since we got a negative here, we'll just bring that out front. It becomes a minus x to the 5th sine of x. And that's it. Okay, using rules you already know with these derivative of trig functions, and get you the answer. All right, let's try another one, or a couple of them. All right, let's look at these two. All right, let's actually do B first, because A, we'll talk about that in a second. It's a little tricky. All right, so for B, I've got two parts. I got 4 tangent minus 5 cosecant. It's not multiplied. It's not divided. It's just a subtraction in the middle. So this will just take the derivative of the first part, derivative of the second part. So let's do it. Okay, the first part is 4 tangent x. Okay, so the 4 is just a coefficient, so just write 4 down. And then the derivative of tangent, if you look back in your notes or you haven't memorized already, is secant squared. Okay, because tangent goes to secant squared. All right, then we have minus the 5 and the derivative of cosecant. All right, the derivative of cosecant, if you look back, is going to be the negative cosecant x cotangent x. All right, the secant and the cosecant have 2 parts to them, and they have the part that was started out and a tangent or cotangent depending on which one it is. Since it's co to start off with, it's negative. All right, again, just some quick cleanup here. We'll have 4 secant squared x, and then negative times a negative gives me plus 5 cosecant cotangent. And that's it. Okay, of course, they could get harder. They probably will. All right, but that's going to be a simple problem there. All right, now we come over and deal with the sine squared. Okay, the hard part about this is realizing our notation. Okay, sine squared x actually means, and you might want to write it out until you get a hang of it, sine squared means the sine of x, and that whole sine of x is squared. I mean sine times sine. All right, and then once you see that, you realize, hey, this is actually going to be a chain rule. All right, my outside part of this function is the squared. The inside is the trig function, the sine. All right, so you got to apply the chain rule. All right, so to find the derivative, using the chain rule, if you remember, it's the derivative of the outside, which is the squared part. So the squared part, the 2 would come down. All right, and then that would subtract to 1. And we leave the inside alone. The derivative of the outside with the inside still there. All right, and then times, we got to take the derivative of the inside. All right, so the derivative of sine, which we look back, or we have memorized, is cosine. So again, chain rule, derivative of the outside, which is the squared part, that'll be a power rule. 2, leave the inside alone, subtract 1 from the exponent, which was 2, down to 1. And then for the inside part, we need to take the derivative of sine, which is cosine. All right, and then we can get rid of the exponent of 1 and just simply rewrite it as 2 sine cosine. All right, and that's pretty much it. Okay, you might see this on an answer to a multiple choice test, possibly using some trig identity, which I might show you in class. All right, if you have 2 sine cosine, that's actually the same thing as the sine of 2x. Okay, if I'm asking you to do it for yourself, this answer is fine. Okay, but we'll just realize that, hey, those are actually the same thing if I see it on multiple choice. And remind me in class to show you why these two things are true. It's a double angle identity, which we just didn't get to last year. All right, so those are those two. Now, we talked about that last one, had the sine squared in that weird notation, rewriting like this. So look at these 3 examples, and notice they're what? Very similar. All right, so we got to be careful to distinguish between similar notations. This first one here is the cosine of x cubed. That cubed goes with the x. Okay, so it's going to be a chain rule, but different from the previous one. This one right here, the g of x here, is the cosine of x cubed. Having that 3 next to the cosine tells me that the cosine part is cubed. All right, that's why we write it there instead of afterwards, so that we can distinguish between the two. And the last one here, you have no exponent, but this is the cosine of 3x. All right, so each one of these is going to be a chain rule, but they're all going to be slightly different. All right, in this first one, our outside is cosine. The inside is x cubed. All right, so when we do our chain rule for our derivative, all right, we take the derivative of cosine, which is a negative sign, all right, with the x cubed still inside. All right, that was the derivative of the outside, the cosine was turned into a negative sign with the inside still inside. All right, and then we take the derivative of the inside and multiply it by this, so that's going to turn into times, bring the 3 down, subtract the 3 down 1 to 2, so it gives you that, which I'm going to rewrite by putting the 3 and the x squared first, and so it turns into my final answer of a negative 3x squared sine of x cubed. Parentheses, not necessarily. Don't necessarily need those. All right, for the g, I do similar to that sine problem on the previous page. All right, here my outside is the cubed, and the inside is the cosine. So it's still a chain rule, it's just the outside and the insides have flipped. So when I do my derivative here, all right, the outside is the cubed part, so it's going to be 3 times the cosine squared, because the 3 comes down, 3 minus 1 will be 2, times the derivative of cosine, which is a negative sign. See how that's different than the previous problem. All right, and then we can clean it up a little bit by putting the negative out in front. And I would probably write my answer as a negative 3 sine x cosine squared. Okay, just wrote it in a slightly different order. Brought the negative out front. Sine and cosine, it really doesn't matter which order you put them in. I prefer having sine first. And then I rewrote this cosine of x squared back as a squared next to the cosine. All right, and then finally on this page, let's do the cosine of 3x. Again, another chain rule. Our outside is the cosine. Our inside is the 3x. So when we do the derivative here, all right, we're going to have the derivative of the outside. So the derivative of cosine is a negative sign with the 3x still inside. All right, and then we do the derivative of 3x, because that's the inside part, so times 3. Okay, because if you have a coefficient times x, the x basically just goes away, and you're left with a coefficient, which was 3. And we clean it up a little bit by bringing the 3 out in front, so we get negative 3 times the sine of 3x. And again, I didn't put the parentheses because you don't have to have them there. So 3 very similar looking problems to start with, but the answers are 3 entirely different things. All right, you might want to go back and look at that a little more. All right, it's going to be in this part. I'm going to do a second part in a second.